All right. Let's see if we get pulled up on the site. Make sure everything's working all right. Make sure we're capturing what we need to capture. Oh, looking good. All right. Yeah, no, we're good. Dun, 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 dun. Except I lost my... I need to pop out a chat room just in case. Just in case. There we go. Because I lost mine. My OBS. I misclicked something. All right, we're good now. So yeah, today we're gonna cover a little bit of what we covered yesterday, just to go over and get a little bit more depth to the different routing protocols, most specifically the Ospf, as it is the most common, and it's going to be the one that's going to be on the Cisco certification. It's going to take up the most of the routing protocols. So it's the one you definitely want to know if you know any of them. And because it's the most common when you're out at work too, so it's not just for the certificate. It's also for, you know, making sure this makes sense for what you're going to be doing with it. So yeah, just some basic troubleshooting. This is super simple stuff. I'm not entirely sure why it was brought up when it was brought up within Neil Anderson's course, but it was, so I'm just going to cover it to cover it. So ICMP, the Internet Control Message Protocol, that's a specific protocol that you can turn on or off at your routers. A lot of times you'll turn them off to stop people discovering inside your network or malicious activity. So this is a way that you can stop like certain kind of DOS attacks, things like that. Like when people are trying to target you and just hit you with a bunch of requests, it can actually bring down your service as it overloads the memory buffers, and it also just overloads the bandwidth. But it also allows for a couple of really cool commands that are really commonly used when you're working within networking. And the first of those is actually ping. Ping tests connectivity between two devices. So if you have someone that's complaining about a service not being able, like they can't reach the local in-network server, first you'd want to test the loopback just to make sure that the TCP UDP was running correctly on that device itself. That'd be a 127. You'd ping that. That'd come back. If that came back positive, the next thing you'd ping is you'd ping the server that they were trying to reach. And typically what happens is if you can get a device, or if you can get a connection with that device, then you're going to get packets returned. So it's going to show you something like 3 out of 5 packets returned. If it knows the address well, if it's within the routing tables, and there's no packet loss, it's going to be a 5 out of 5. You know, that's just based on how well it has the connection to the device. But as long as you're receiving packets back, that means that you should have connectivity. So that's just a way to test that. And it means then you're going to have to move on somewhere else with your troubleshooting. The problem is elsewhere. Traceroute is another really great command that falls under the ICMP. So Traceroute does the exact same thing that ping does, only it uses the TTL, which is the time to live. So every packet that's sent out over the network is given a TTL. And that TTL is to prevent the network from becoming overburdened with packets that just have nowhere to go, right? So if you send something out, if you send out like a broadcast and it's going somewhere that doesn't exist, it could end up, if it didn't have a time to live, it could end up just ricocheting between two switches just over and over and over and over again. And if that client keeps sending out broadcasts and those packets keep getting trapped and just going back and forth between two switches, it won't be long before you overload that connection. and then your network's down. So time to live, every packet comes with one, but Traceroute uses it, so it gives, it's essentially like putting together a bunch of pings. So the first time you use Traceroute, it's going to send a packet out that only has one in the TTL field. So it's going to go out, and the first thing it hits, it's going to die at. So that device is then going to send a response saying, yeah, your packet got here, but it died. Then Traceroute is going to send out another packet with a time to live of 2. So it's going to go to the next hop. It's going to get through that first connection. It's going to go to the second one. It's going to die. That device is going to send back a response saying, hey, your packet got here, but then it died. Traceroute's then going to send out a time to live of 3, and it's going to keep doing that until it hits the actual device that you're looking for, or until there's like certain arbitrary TTLs that you don't want to run into. Like if it takes too long, like you got to find a different route. But that's a way that you can. So with ping, you're just seeing that you have connectivity to the end device. With Traceroute, you're seeing that same connectivity, but you're seeing all the steps in between. So that's a really neat way that you can actually ensure that your packet is taking the route that you want it to take, not only getting to the destination that you want it to get to with. Again, one of the reasons ICMP is sometimes disallowed is because Traceroute is a great way to map out networks. If you're like a malicious actor, you can get inside and then you start sending out traceroutes, and you can literally map out the topology of that network, and then you can further attack in. So that's why it might be turned off. So that was just a couple of I didn't even fill out what this is. Traces the path each packet sent out is increased TTL by 1, allowing you to see each jump. What would we say? Mapping the network. Yeah, that's fine. So that was a weird little, like just a 10-minute lecture that was put in the middle of all this routing stuff. So I included it in my notes because I did go through it, but I don't know. You just go with it. So what I also covered is yesterday we covered routing protocols. We covered interior, exterior. Exterior only has one. It's going to be the border gateway. Interior has a lot of different routing protocols. Most of them are no longer in use. For instance, RIP is very rarely used, mostly for test environments, or for maybe like legacy systems where they just don't have someone in networking to be like, hey, you shouldn't use that. ISIS, I should say RIP and I just blanked. I was doing this from memory. RIP and what was the other one I was talking about? Now I gotta find it, and it's all taking me forever. OSPF, right? Was the other one I was talking? Well, RIP and EIGRP. EIGRP would probably be more popular, except it's Cisco specific. It has recently become open source, but a lot of vendors just don't bother putting in the support for it. So a lot of people just stick with OSPF. That's still why it's the most common. But again, RIP and EIGRP are actually distance vector routing protocols, whereas OSPF and ISIS are link state routing protocols. The difference being the metric they use to determine the best path forward when they're when they're choosing between multiple routes to the same destination. All that in mind, what I was saying is some of these are not even really in use anymore. So RIP, again, not really in use. EIGRP can be in use as long, it might be in use if that network was traditionally all Cisco, so they could do it anyways before it was open source because everything was Cisco, so it didn't matter. It probably even worked better since it was all Cisco. That might be a reason that you would see that. The other reason being now that it's open source, some companies may have chosen to move over maybe because they have other Cisco operations. Like, for instance, Cisco's VoIP phone service is really popular, especially in like government. When I was in the military, we used Cisco phones, and when I was in the National Park Service, we used Cisco phones. So that might be a reason that you'd be seeing Eigrp, just because all that Cisco, all those Cisco devices can communicate on that protocol with no issue. Otherwise, it's almost guaranteed that you're going to see OSPF, the open shortest path first. That's pretty much the most common routing protocol that you're going to see. So that's actually why I'm going to dig further in to OSPF, because it's really the one to focus on. So let's see here. Let's just just write up what we know for sure. OSPF is, it falls under the IGP. That's the interior, so it's not an exterior protocol. It's going to work with inside your network. It's also link state. It's a link state routing protocol. And the cost metric it uses, I believe, is it's, I think, two things, but it's mainly the bandwidth allocation on the connections, on the interfaces. And again, the lower the cost, the lower the number, the better the connection. So actually, really quickly, what we can, well, no, I don't think I'm there yet. Actually, yeah, we'll come up on that. So I'll try to remember to tie it all in. But so Ospf operations, what happens when you first plug one in? Well, you're gonna plug it in, find that period, and it's gonna start discovering, or not when you plug one in, because it's not a device itself. When you enable OSPF on an interface, because that's what you do, or on all the interfaces, either way, the first thing it's going to do is it's going to discover its neighbors. So if it's on an interface, it's going to send out a hello packet on that interface. And what that does is discovering neighbors allows it to form adjacencies. So it's going to send out a specific packet on that interface. Any other switch on that interface that's or switch or router on that interface, any other router, sorry, it's a routing protocol. Any other router or layer 3 switch on that interface that's using OSPF will then, it will receive that hello packet, and it will, from that hello packet, it will be able to form an adjacency. So this is kind of, we talk about how it's a link state routing protocol. We talk about how OSPF is able to see the entire topology of the network. This is how it goes about doing that. So the third thing it's going to do is it's going to flood the link state database. And this is just, we'll find out a little bit later on what the link state database is, but it's essentially like what that, so it's going to take everything it knows about its networks, and it's going to send it out to any adjacencies that it's formed. So it's saying, hey, that's what the flood means, because it's sending it out to everyone. And then what it's sending is the link state database. And that's just saying, this is what I have access to, and this is what the cost metric is for me. So if you were to send it through me, you'd add on to that. So the next thing it's going to do is, now that it has new information, it's going to compute new shortest paths. Once it's able to compute the best paths, it's then going to install, or it's going to update its best routing table. So again, we're enabling OSPF on an interface. It sends out a hello packet. Anything else on that link that is working on OSPF, any other router, is going to form an adjacency with it based on that hello packet. It's then going to flood a link state database back to it. It's going to say, hey, here's the networks I have access to, and what it looks like. that's going to update the router's topology of the network, its ability to see what's around it. Based on that update, it's then going to compute new paths, and it's going to look for the shortest, the lowest cost, the best paths that it can possibly find. It's then going to install or update those. We're saying this is brand new, so it's going to install those routes to the routing table. So now the routing table has figured out the best routes that it can use based on all the information that it's gotten. It's then gonna, the neat thing about OSPF is it has an ability to respond to network change. So again, so what's gonna happen is if one of these devices, like there's a new person on the network, so they plug in to the switch, that's gonna add a new destination. So that device is then going to send out a flood link state, but instead of a database, I think it's like an update, or no, it's an advertisement. It's going to send out a link state advertisement saying, hey, this changed. And sometimes it's like new stuff being opened up, new switches being added on, new end host devices being added on. Sometimes it's things going down or being taken off, right? So if, like, for whatever reason, one of your physical interfaces fails, based on whatever reason, like the physical line fails, the Ethernet port fails, it just burns out, or maybe the whole device fails. At that point, all the routers around it that are working on the OSPF that have lines, links that are shared, are going to update their table saying, uh-oh, this just changed, and it's going to flood it out. So that's really cool that it's able to do all this kind of in the background, right? You enable this ability, and then you don't have to worry about, like, oh no, something just went down, I have to update all these static routes, right? So that's the great thing about having these protocols that are dynamic, responding to network change. So I talked a little bit about packets earlier. Let's talk a little bit more about them. So I said hello packet. That's the first packet that OSPF uses. So once you enable, once OSPF is enabled on an interface, it sends out hello packets. Oh, sends out and listens for, right? So it's not just sending them out, it's also listening for hello packets, because maybe it just got turned on and maybe another switch just got turned on next to it. So it needs to be listening also. It needs to be forming new adjacencies, even if it's just got enabled on this interface. This is how the devices form adjacencies. And again, this is with other routers, because it has to be routers. We're talking about routing, or layer 3 switches, I suppose. And it has to be on the same link, on the same line that's coming out of that interface and going into the other interface. It has to be on that link. Another packet type is the DBD. That's the database description. The DBD sends all known networks to adjacent routers. So this is what's going to happen. It's going to send a hello. It's going to say, hey, yeah, I'm also using this OSPF routing protocol. Let's be buddies. So they're going to form an adjacency. The next thing that's going to be sent is a DBD. It's going to send all those networks that the router is aware of, that it has access to, and it's going to share those. And then what's going to happen? Nope. Well, I guess, yeah, let's go down to the bottom. So let's go to what's going to happen next is LSA LASARC. This is an acknowledgement. So, oh wait, no, this is wrong. This is not what happens after a DBD. Ignore me. This is what happens after an LSA, which is a link. Let's get this right. Link state advertisement. So this is actually, we were talking about when something is added or something goes down, it sends out a link state advertisement. This is to, we'll call this routing update, like just saying something's changed in the routing, right? So once it sends out an LSA, any device that's, of course, using the OSPF is going to send back an LSA ARC, which is acknowledging that they received that that advertisement, that routing update. There's also the LSR, which is link state request. This is if the router is missing any information in the DBD. It sends back LSR as a response. So let's move this up under the DBD just to make it a little bit clearer, which is where it was gonna be until I confused myself. So yeah, OSPF packet types. This may not be all of them. This is the ones I've learned thus far. We're going to start out with a hello packet. The hello packet is what allows you to form adjacencies with other routers using that same routing protocol on the link. At that point, you're going to get a database description that's when a router sends all the available networks it has to it to the adjacent routers, allowing them to update their network topology. At that point, if they're missing anything, they're going to send back a link state request. And that's just saying, hey, you sent me this DBD and I noticed you have a link that I don't have. I would really like it if you could send me some more information on that. The LSA is a link state advertisement. That's just when something changes, it wants to update all the other routers. So it says, hey, something changed here on my router or just right next to me on this link, and I need to update everyone else on it. At that point, everyone who receives that link state advertisement is going to send back an LSA ARC or LSA ACK, which is an acknowledgement sent back from an LSA is received. And I think I might be describing this a little bit wrong because, again, this is just going to be connections between adjacencies. So if you think about it, it's going to be like, it's not necessarily like you're not going to get a LSA ARC from a router 2 or 3 hops away. You're just going to get a LSA ACK from the routers directly next to you 1 hop away that are on that same link, and then they're going to get it from the routers that are 1 hop away from them on the same link, and so on and so forth. That way you're not like sending too much information over the network, but you're still able to update. And the acknowledgement would be kind of like a checksum, like making sure that nothing corrupted. So that's all interesting, right? Another thing I learned about today was administrative distance. This is a little weird. I'm still making my way through this stuff. So this is used when 2 different routing protocols. So if a company, for whatever reason, and I don't think this would be very common, but for whatever reason, a company decides that they want to use both OSPF and ISIS. And so if they're using both those routing protocols, and both those routing protocols happen to make it to the same destination, administrative distance is what is going to have to happen at that point, because the system can't decide between 2 routing protocols which one's better. Like it just, for whatever reason, it can't make that choice. So it has to use this administrative distance. And what AD does is it chooses the route with the lowest administrative distance. That's kind of a bad definition using the word in the definition, but come on. So you can change the default administrative values, but if you want to look at what they default to, this is, let's blow this up. Here we go. This is what they default to. So if it's connected directly to the interface, that means it's not, it's plugged directly into that device. It's a 0. And again, the lowest number is the best. So of course it's a 0 because it's right there. If it's a static route, if it's one that you've plugged in or one of your network administrators have plugged in, that's going to get preferential treatment as well. So that's going to give it a 1. So this may not technically be the fastest or the the best route when it comes to the metrics, but it's the one that your network person has chosen, right? So they're like, we really want you to use this one. External BGP, that's going to go to 20. This is the border gateway protocol, the only external routing protocol. I'm not entirely sure why it gets put above the others. I'm sure that'll make sense to me later. I guess, I don't know why you'd want to send it, you'd want to default to sending it outside the network before you did any of these others, but okay, I'll figure that out later, I'm sure. Eigrp, this is the Cisco specific one that is now open source, but is still known as what was initially Cisco specific. It actually has one of the better so it actually has the best out of all the internal routing protocols, right? But again, because it wasn't open source, it's not as common as OSPF. So this one is actually rated worse, but it's more commonly used. So what are you going to do? Then we have ISIS at 115 and RIP at 120. So if it defaults, it's automatically pretty much guaranteed this is your default for administrative distance values. So if two protocols come in going to the same device and it has to choose between which one it's going to use, it's going to go to this default value list unless you update it with your own values, of course, and it's going to choose based on this list. So that's just something to keep in mind. So again, this is used when two different routing protocols could be used to reach the destination, and the system then has to choose I wouldn't say the best route. Let's say system uses 80 to choose the protocol. Yeah, so that's accurate. So 80 itself is not a metric, but it has it's a table of metrics, right? Like it's not a specific metric. Let's see here. Loopback interfaces. This is something else I learned about today. That's kind of neat. So a loopback interface does a couple of things. One thing that it does is it's one way that OSPF gives the router an ID. So if you put a loopback interface on your router and you're using OSPF, then it will it's like a name for the router. So it's a better way to map out your network. It also is a way it's a way to, what did they say it does? It like gets rid of traffic that's not going anywhere. Yeah, commonly used for traffic that terminates on the device. So this is like management traffic, like updating the router itself, VoIP, BGP, peering, etc. This is stuff I'm not really too sure about, but this is, you got to learn what you're taught and then kind of put the pieces together as you learn more. But basically, it's used a little bit for that, for traffic that terminates on the device, but more so it's used as a router ID. It's also really neat because as a router ID, it's a logical interface. Logical interface means it's not physical. It's not physically on the device. It's not a VLAN. It's a virtual interface, but they call it a logical interface. So that means that, unless the router itself goes down, that loopback interface won't go down. Like, unlike a physical interface that can break for whatever reason, or the line to that interface can break, the loopback interface won't break. And why is that important? Well, if you're using it as the ID for the OSPF, then if you were using a physical interface and it breaks, then all the other routers have to be updated. And not only that, the router name changes. Like, it causes a lot of issues and can cause routing problems, right? Whereas if you're using this logical interface that doesn't go down, that doesn't change, it really helps with the stability of the OSPF routing protocol. So it's best practice to enable a loopback interface on your router. And you typically want to assign, I mean, you can assign it any IP you want because, well, it's not even really an IP, but you use an IP format. But really, you can assign it anything you want. But best practice, again, is to use an IP that would fall within the subnet that's managed on that router. Again, that's just to make it easier to follow logically when you're looking at a network map. But that's not necessary. I mean, if you wanted to put 1.1.1.1, 1.1.1.1, that's fine. That's just how that router would be ID'd. So loopback interfaces, we'll say this is a logical interface. Again, that means it's not physical. Not tied to a physical interface, can't go down. It's also commonly, it defaults to a /32, which is in dotted decimal would be a 255.255.255.255. So it doesn't go anywhere, right? There's nothing to it. And that's to avoid wasting any IPs. Also used in OSPF to as the router ID. Yeah, we'll say it like that. That's a good way to say it. We're working on it. You can have more than one you can have more than one loopback on your device if you need to terminate special traffic to a specific address, and you want to make that its own specific loopback separate from the other one. You can do that, but that's going to be very specific to some type of software program you're using. So again, that's not something that you should really worry about on the Cisco test. That's more something that you'd work on in the real world, but hopefully you're working at a place that would put this stuff through some kind of process. So before you got that program, before you even purchased that program, you'd understand what was necessary to run it on your network. You had already thought all this out and built it all out, or said, no, we don't need this because we don't need to put a bunch of extra loopbacks, for whatever reason. It's just, hopefully people aren't just slapping stuff onto your network willy-nilly, because that would be a nightmare. Let's talk about adjacencies, even though we already did, but since that hello packets, you know what? I already went over all that. Adjacency is the routing protocol. When the routing protocol is enabled, the interface sends out hello packets. It receives a response. That's how it creates an adjacency. This, of course, is, again, dependent on them both using the same routing protocol, both being on the same link. Apologies. I've been drinking a lot of soda to keep energized, and you know how that goes. Then exchanging routing protocol. So that's all the adjacencies. That's probably something I do need to learn, so it might not hurt to continue to take notes on it, but I just did above this, so let's not go too far into that. There's also, here we go, passive interfaces. This is something I haven't covered yet. Passive interfaces, so adjacencies are always going to be updating everyone else, and that's spreading information on your network. But sometimes, like for security reasons, you may not want you may want to include that next router's over network information within the overall topology, but you don't want to send that router network updates. So you want to get the network information from the next router over to add to your topology, but you don't want to send any to them. And that can be because that router is maybe outside your physical control, but still owned by you, or maybe it's owned by another company that you work really closely with. So you want to have that connection with them. You want all your routers to be able to route very cleanly to them, but you don't want them to have information on your network. You don't want to give them the overall topology of your network, which that's a good practice. So to do that, you would enable a passive interface. So this allows you to include the IP subnet in the routing protocol without sending updates out that interface. So again, you're collecting that router's information and you're passing it on to all the routers behind you, unless they're also passive, but that would be ridiculous. So we can think of this almost as like a line between a demilitarized zone, DMZ. We use DMZs a lot in networking, even though, whatever, for whatever reason. We can think of this as a DMZ. So there is a connection between these two routers, but we're going to control what information passes. So we're going to collect information. We're not going to send information when it comes to this routing information. So that is good stuff to know, especially with security becoming more and more important. Knowing how to do things like passive interfaces, I feel like is helpful. So loopback, going back to loopbacks, loopback interfaces can also be made passive, which is good because you're going to be sending stuff down loopback addresses, all that information that you want to terminate. But there's nothing on the other end of a loopback address. It's just a logical address, right? It doesn't go anywhere. It's just a way for routing protocols to name the router, and also for you to, I'm sorry, I keep bumping my microphone, and also for you to terminate that data, those packets, right? So you'd put passive interface on there because you don't want anything waiting for a response. You don't want them being like, all right, where's my acknowledgement? I'm not getting an acknowledgement. Send something else back out there. So you name it passive, and then they're going, okay, we're not expecting anything to come back. That's essentially what you're doing to that loopback address. Boom. So you're going to use passive on loopbacks, and you're going to use it when there's like devices outside your control or owned by another company or shared with, you shared network access with someone else on that one, and you don't want them. There's a lot of reasons you do it, but it's essential to that. All right, let's also talk about VLANs. Yeah, VLANs are awesome. To understand VLANs, though, we have to kind of build our base up, our base understanding. So the way Neil did this is he first talked about a campus LAN. So a campus doesn't necessarily mean like a college. A campus is like, but it's like a number of buildings that are somewhat close together, but are not necessary. The network isn't all essentially shared within one building necessarily. That's a good way to put it. But it's also not like super spread out. It's not a WAN. It's not like across continents or even across states or anything like that. Like it's very, maybe it's like, I think there's even a different term for across cities. If WAN might even be citywide. So yeah, let's just keep it like within the same block or something like that. Campus LAN. So the base layer, the layer just above your end host, so like your people on desktops, your people on laptops, your servers, the layer just above that is going to be your base layer. And the base layer is actually going to be called the access layer. And this is all for switches. Everything we're talking about right now is about, what are my switches? Whew, man, all right. So we're not talking about routers here. We're not talking about hubs. No one's ever talking about hubs. We're just talking about switches. And the access layer is the layer just above the end user, just above the host. This is where end users, hosts, desktop, all that stuff, this is where they plug into. So this is going to be like the first switch that an end user has contact with. That layer of devices is the access layer. So apparently client access security measures can be enabled at the access layer. I don't think I've actually gotten to the course, the chapter that talks about what that means, though. So I think that's later on in security, I'm guessing. The CAS, client access security. Maybe it doesn't even default to CAS, but that's something I haven't quite learned about. So the access layer, again, is the first layer up. The next layer above access is the distribution layer. And again, switches, let's keep that in mind. This serves as what's a good word? Aggregation. This is an aggregation point. This is where all the information from the access layers is gonna come to. So the access layers are getting fed in. They're end users, hosts are feeding into the access layers. All the access layers are feeding up to the next layer, to the distribution layer, and they're all aggregating their information there. So there's often, you're going to deploy these switches in redundant pairs. So you're going to have the switches below, you're going to have them going to two different switches above. That way, if one drops, they have another pathway up. And that redundancy is, again, for security, but also just to keep your network up in case of one of these switches going down, which is going to happen. You're going to lose switches every now and then, power outages, whatever. The device just drops out on you for whatever reason. So these kind of redundancies are going to keep your network up. And that's why it's built this way. So this is your aggregation point, we'll call it that. It also has redundant pairing. You're not going to see any end users connected to this level. Directly connect, let's say directly. Because they'll get there through the access layer, but they're not going to directly connect up into the distribution center, unless it's like a specific server or something like that you need hooked up that way. But more often than not, you're not. One of the things we can do on the distribution layer is software policy can be enabled. It can be enabled on any level, but this is typically where you would see it enabled. And the most common form of software policy is QoS, quality of service. This is something that I haven't reached in Neil Anderson's lectures, but I've covered in other things. And this is just how how you give different data different priorities, UDP, TCP. So you want to give like your VoIP a higher priority, because if you drop VoIP packets, it's going to cut out the phone call. So that kind of thing. That's going to be enabled at the distribution layer. Next layer up is going to be your core layer. Again, talking about switches. So you have end users, people on their desktops, laptops, whatever. They're going to be dialed into the access layer switches. Those access layer switches are then going to aggregate all that data up into the distribution layer. The distribution layer is then going to provide some kind of software policy on it, prioritizing data. At that point, it's going to shoot that further up into the core layer. So the core layer is also going to have redundant pairs. Just in case, because if one goes down, you're not going to lose your whole network again. You're just going to lose that switch, but your network is going to be sustained. You just might have heavier loads on the remaining links. But the core layer is also, it's built specifically for speed and resilience. Because at this point, you've already done all your prioritization, you've already done your access security measures. So when the data gets to the core layer, it's already been organized. They've already thrown out the stuff that shouldn't be there to begin with. So at this point, you just want it to get to the point it needs to get to as fast as possible, but also make sure that this portion of the network doesn't go down. So resiliency, it's got that ability. If you lose one switch, you got more switches that can pull up that dropped data, that dropped network. Carry the load. That's what I should say. So that's just a basic kind of campus LAN design that smaller businesses probably won't have a distribution and a core layer. They might combine those, but there's still going to be an access layer. It's just a good way to secure your networks, to ensure that your end users have to plug into this one layer. It's just good security procedure. I'm sure it's good for other things as well, bandwidth management, things like that. But I always think of security. So another thing we're going to talk about is spine leaf, and this is data center design. So this is kind of like using the same design principles, but now we're talking about virtualization data centers, because virtual machines are very typically in data centers because they just need all that processing power. So this is actually the neat thing about spine leaf is it talks about the two layers it has. It has the spine and it has the leaf. So let's talk about it like we talked about the other one from the bottom up. Leaf is going to be your access layer where all your servers are tied into a switch, or duplicate switches, of course, because you don't want to. Well, actually, at this layer, it would probably just be tied into a single switch. At the access layer, that would make sense, yeah, because you wouldn't want to give it two IPs. Yeah, so access layer is where your servers are tied into a switch. Oh, the interesting thing about these switches is they connect to every switch along the spine. Whoa. So we'll talk a little bit about that in a second. The spine is the second layer, your second tier in a two-tier system. So this is your higher layer. This is going to be so the reason that the every switch on this layer is going to have a connection to every switch that is connected to a server on the layer below. Whoa, does that make sense? It does, but does it? So why would you do this? Well, that means when you're transferring data from server to server, no matter what server to what server, like how far along the leaf you are on either direction. So if you're going left or right, because you're just constantly going further and further out, you have more and more servers, right? No matter how far apart those servers are when we're thinking about it on the leaf, they'll be 2 hops away by the time it gets to the spine, right? Because it's going to go boop, boop, because it's connected. I mean, it's so much easier to do this with pictures, but I don't have time to like come up with graphics and stuff. I'm like studying right to the point of I stream. But yeah, when I'm studying that, remember the pictures. So really great. It's great for like keeping it speedy and also keeping it like keeping the connections up. So it offers it's great for data centers and virtualization because especially with virtualizing programs, as your demand goes up, you just spread that program over more and more servers. So with the spine leaf, you can just go left and right with it, but it doesn't ruin your connectivity because you're always those 2 hops away. So it's an amazing, like, whoever thinks of this stuff is more power to them, man. Amazing. So have we actually talked about VLANs yet? No, we haven't. We've just gotten to this point where we can actually start talking about VLANs now that we know about this other stuff. So a VLAN is an access port configuration. This is done with Cisco on the CLI commands. So doing it using PuTTY or with Packet Tracer, you just go to the CLI command tab. So what we would do to make a VLAN on a switch, well, let's say we got switch 1 here. We would, of course, enable it to reach privileged executive mode. At that point, we would want to configure a terminal because these VLANs are virtual LANs are on an interface, like just like a routing protocol, they're configured onto an interface. That's the way to say it. So at this point, we would reach the config global configuration level within CLI. At this point, we can actually create the VLAN. So we're just going to do VLAN, and then we're going to give it a number. Now, this number, you're probably going to want to like have it all planned out on your network topology, but it can be anything. So we'll just call it like 15. So this is VLAN 15, and then we can also, let me see here. Make sure that you can, because I'm pretty sure you can give it a name. Yeah, so once you give it a number, it's going to drop you into, I'm not sure exactly what this is called. It's no longer global, I guess it's VLAN configuration. That makes sense. That makes complete sense. So at this point, we can give it a name. We can say name followed by whatever you want to call it. So a good name is going to be based on what the VLAN is servicing. So a lot of times it's going to be like a specific network that you want to be separated from other networks. So you're going to say like your HR team. So the name's going to be HR. That way you can look at it, you can be like, oh, that VLAN is specifically for HR. That makes sense, right? Or for sales or for accounting. Like there's reasons that you'd want these to be separated. So at this point we can go, we can actually configure it to a specific interface. We go configure interface. So what were we doing here? We were just creating a profile for a VLAN. So we haven't actually pushed it onto an interface yet. There's this VLAN that we can use. We can put it on different interfaces, but it hasn't actually been associated with an interface yet. So what we can do is we'd actually drop down. So at here we would say end, and it would drop us down to back into the global configuration menu. At that point, we could pull up a specific interface. So we put interface, and for this example, we're using fast Ethernet 01. We're going to go back into configure interface mode because we pulled up this interface, so that's what it's going to do, of course. And here's a new command I learned today. We're going to do switch port mode access. So this is going to make this port, it's going to put it in access mode. right? Okay. And then we're gonna do switch port access VLAN 15, because that's what we named it. So we're accessing a port. We're getting into the configuration of a single port on this switch, and then we're enabling access mode on that switch. And then once access mode is enabled, we're putting that VLAN profile that we created above onto it. So this switch is now accessible via access, and it's running VLAN 15. Or this specific interface on this switch is in access mode, and it's running VLAN 15. Whew, all right. A lot of times you're going to be putting VLANs on more than one interface on a switch, because you're going to have more than one end host, more than one server on that switch that's being accessing that VLAN. Like HR isn't just going to be one person. Typically, it's going to be a number of them. So you're going to want to do this for a range of interfaces. And there's no reason to go through and be like, interface fast Ethernet 1, interface fast Ethernet 2. So instead what you can do is you can put interface range fast Ethernet, I think there has to be a space there, space 0, 1, and then you can do it through like, you know, you got 24 port switches, so you can do it all the way through, but you do it through like 12. You don't put a 0/12 on the second number. You just put the ladder number, and I think that's because the 0 probably throws off the system. It's like, why are you going to 0? 0 is nothing. So you just drop that, and you put the second number within the interface information. And then you're just going to do the same thing. So then you're just going to run this command again. But at this point, it's going to be doing it for all 12 of these interface ports. It's not going to be doing it just for one. It's going to turn them all to access ports, or all to access interfaces, and then it's going to plant the VLAN 15 as that access. Again, you want to try to decide these VLAN names and VLAN numbers. You want to try to figure this out beforehand. You want to have like a really good idea of how you're going to map out your network, so you're not like creating these willy-nilly and making it really hard for someone else to come through and figure out where things are going or why things are named why they are. A lot of this stuff should be pretty logical, right? When it comes to naming, the numbering is not necessarily logical, but you can do it like 1, 2, 3, 4, 5, like as you're working on like something like that. I'm sure there's some kind of logical means to it. So another thing you can do, what we've been doing is VLAN access up to this point. We can also do VLAN trunk ports. And this is, I don't know if it's ports, I think it's interfaces. VLAN trunk interfaces. Ports doesn't sound right. I'm gonna look that up later. So trunk ports, so these accesses, they only cover one VLAN, right? But if you had two switches connected to each other, there may be more than one VLAN that needs to transfer information over those. So instead of having an access port with a single VLAN associated to it, what you can do is you can do, and I called it a portgen. Instead of having a single access interface, you can have a trunk interface, and that allows multiple. Oh, thank you, spell check. Allows multiple VLANs to cross the same interface. Pretty cool, right? And that's why it's called trunking. You can think of it as like the trunk of a tree. So if the accesses are the branches, you know, just single VLANs, they come together in this trunk where a bunch of VLANs can all go across at once. So a lot of times just these silly little thoughts are what actually helps me on the test. I think trunk, tree. Oh, more than one VLAN. That's right. Covers all. So how it does this is it uses .1q. There used to be another standard, but apparently everyone uses .1q now. So .1q, get it. It's the standard for trunking. And what it does is it's a header. Oh man, it injects .1q trunking information into the Ethernet header. So if data is coming into this interface and it says, hey, I need to take this trunk port, and everything checks out, it's like, hey, yeah, you're right, you got a VLAN on this trunk interface. We need to send you down it. But in order to make sure that you don't get confused with the other VLANs, we're going to inject this one little piece of information in the Ethernet header that tells which VLAN you're associated with. So all this information that goes over this interface is going to have this one little piece of information injected that shows which VLAN it should be associated with. It's going to go on the other side. The switch is going to pull out that little injected piece, and it's going to say, okay, you're VLAN 15. For us, we'd call it HR because that's the name. It's going to send it down the interfaces that are associated with VLAN 15. Another piece is going to come across, is going to say like VLAN 21. You're going to be like, okay, that's sales, so it's going to send it down those sales interfaces. If it comes to a point where it's sending it directly to the end user, it's actually going to pull that information out, because end users don't need to know anything about VLAN, right? But as long as it's being sent down these trunked ports, it's going to keep that injected data in, is how I understood it. I'm pretty sure it doesn't keep pulling out and injecting it. I think it just keeps that injected header information until it gets sent down an interface that is no longer maybe no longer trunked is when it pulls, but it for sure pulls it when it gets to the end user. And that's just because that's unnecessary information to broadcast, right? Like the end user doesn't need to know anything about these VLANs, so it's going to pull that out. It's going to open up bandwidth on the line that otherwise would have been taken up. So good information, good stuff. There are sometimes end users are going to get VLAN information that's specific. We'll cover that later. That's like VoIP phones and stuff like that. They'll have because of the way that's connected to the computer. But that's its whole own thing. Let's see. Wow, it's already been an hour. I would go through the VLAN trunk commands, but that just seems like unnecessary, since it seems kind of like filler. So we can verify that these commands have been run. When we're on that switch, what we're going to do is we're going to do a switch. We're going to pretend we're already, let's do it. Enable, we're going to get up to the privileged executive mode. From the privileged executive mode, we can do show commands. So we're going to do a show interface, and then we're going to pick out one of the this is a placeholder for whatever actual interface you're using, right? So that can be any interface that you're actually using. So show interface placeholder, fast Ethernet 01, and then you're going to type switch port. And that's going to pull up all the information that tells you whether it's been truncated, whether it's an access, and then what VLAN is associated with it. If it's trunk, of course, it's going to be more than one VLAN. If it's access, it's just going to be a single VLAN. So that's a way just to make sure that this information has configured properly on your switch. And then, of course, you can save that configuration file, and you'll be good to go. So there's actually, now that we know about trunking, there's actually a dynamic trunking protocol, also known as DTP. This is, again, like many of the things we're going to learn on the Cisco certificate process, this is specific to Cisco. So this is DTP you're not going to find on just any old device. It is Cisco I think only. It may be open source now, but I think it's Cisco only. So this works as long as both devices talking to one another are Cisco, as long as they have access to DTP. So I'm guessing it's not open source yet based on that one little thing that I just read. So DTP allows you to... This will dynamically actually create trunking protocols. Like it will change the switch mode access and switch mode trunk. And it will create those VLANs for you. However, it is recommended to manually configure these switch port modes. Ooh, let's call them that. So dynamic maintaining switch port modes access trunk. Oh, you know what? This might only work for trunk. This only works for trunk. Dynamic trunking protocol. Duh. Specific to Cisco, and it will create trunk interfaces for you, essentially. However, again, yeah, we'll call it that. All right, so however, again, it's recommended that you set up your own, manually configure. Set up your own is how I say manually configure, same thing. Your trunk interfaces. Another thing is VTP, and this is your VLAN trunking protocol. So this one is actually kind of neat. I could see where this one would come in kind of handy. So what VLAN trunking protocol allows you to do is it allows you to add, edit, or delete VLANs on a switch. We should talk about here real quick. Let's just, okay. What's a good? So there's actually 3 types of VTP. So VTP can be a server, it can be a client, or it can be transparent. If it's the server, you can have more than one server, but if it's a server, that's where you can actually do this. You can add, edit, or delete VLANs. And what we're talking about is this part. So when you're creating a VLAN, not pushing it onto an interface, but when you're actually creating the VLAN, creating the number and the name, you can do that from a VTP server, and it will push that information out to it pushes all that information out onto all the VTP clients on the network. So that means instead of making each of these VLANs on each switch over and over and over again, because you're going to need to make that HR one, you're going to need to make that, or some of the other ones I was using, like sales, stuff like that. You're going to have to make those on every single switch because you're going to need to use them on those interfaces, right? However, with VTP, you can just designate one or more than one of your switches as a server, and then you create them on there, and it will push out to all the clients. That being said, even though you can have multiple servers, one server is like the server of servers, and that's dependent on, like, what was the wording he used? Highest revision number. So the server with the highest revision number is like the king of king servers. I don't know what that means. I think that's something we're going to cover yet later on. Highest revision number. And transparent allows you to push that information to pass it along, but it doesn't update that switch itself. So that switch will still receive VTP information from servers, and it can still push it further down line to clients, but it won't update its own VLAN. What would you call this? Like profiles. It won't update its VLAN profiles. I'm not sure if that's accurate, but that feels like a good representation of what you're creating. You're creating a profile. So yeah, that's neat. That's pretty much, there was a little bit more I went over, but let's not go crazy with it. It's already been an hour. Whew, these things are starting to get longer and longer. I think I went for like an hour 50 last night or something like that. I don't know. Let's take it back a little bit. All right, so last night we went over routing protocols overall. We covered IGPs and EGPs. EGP, there is only one option. There's the BGP, which is the Border Gateway Protocol. IGP, we went over 4 separate options, but out of those 4, it sounds like the OSPF is by far the most common, so that's the one I'm going to focus on the most. I'll probably focus a little on the GRP, the Enhanced Interior Gateway Routing Protocol, the Cisco specific one, because this is a Cisco test. I feel like they're going to have a little bit of a want to cover their own stuff. We talked about how they have different routing protocols within those. So there's distance routing, there's link state routing. Distance is based on like how many hops away something is. Link state is based more on like the bandwidth of the lines in between. We went over some basic troubleshooting today. That was ping, traceroute, how they differ, how they're the same. Ping is U to destination, traceroute is U to destination, but it covers all the steps in between as well. We went over a little deeper into OSPF, the operations, how it discovers neighbors, how it forms agencies. We went over the flood link state database. I can't. So flood is what it's doing. Link state database is what it is. I don't like how I wrote that, but it's how I took the note. So I'm gonna have to look into that a little harder. It computes the shortest path. It installs the best routing table once it has the shortest path, and it's able to respond to network changes. So OSPF sounds pretty rad, to be honest. Here's the packet types that we've learned about so far. There's 4 of them. 5 of them, 1, 2, 3, 4, 5 of them. Went over all those. Administrative distance is when you have 2 routing protocols. You need to choose the best one. Loopback interfaces, make sure they're in passive mode. They give you a router ID for OSPF. Yeah, and we just talked about this other stuff. So this is pretty rad. Covered some stuff pretty well today. I didn't get too deep into the labs. I did the labs, but I didn't like really stress myself on the labs. I stressed myself more on this information, trying to remember some of these acronyms, trying to make connections between how some of these systems are distributed, how they're set up, how I can expect to see them in the certification in the test. Yeah, it's looking pretty good. This is day 8. I'm starting to get a little wacky going over all this information all day, but that's to be expected. It's only going to get weirder. Hasn't even really gotten that weird yet. But we'll see how this goes. I'll see you again tomorrow. All right, everyone. Take it easy.